I'm here to talk to you about how the Melbourne Space Program, a student-run, not-for-profit organisation, successfully has just designed and launched our first satellite, ACRUX-1, and how we did that over the last 5 years. So the Melbourne Space Program's a charity educational organisation. And we're about 80% student-run, 80% students, 20% people like myself, people with day jobs, unfortunately, working on the program, and the vision and the reason why the Melbourne Space Program exists really is to develop and foster the next generation of space pioneers. So a little bit about myself. My name's Blake Fuller. I'm the engineering manager at the space program. My day job's working at a company called Hydrix here in Melbourne. Hydrix is a product consultancy firm working in mainly medtech, but also consumer, industrial, and defense. So the majority of my job's working on things like exoskeletons there, life-sustaining medical devices, so things like artificial hearts, and cochlear products. So the Melbourne Space Program actually started off as the University of Melbourne Space Program. I've said here early 2015, but it's maybe even 6 months earlier than that. It's hard to know with these things. So it started off as essentially a student club. Back in 2015, the original goals were a bit hazy, but the club knew that they wanted to build a satellite. They knew they wanted to put something into space. They had a few ideas about technical direction. They had an idea about this self-inflating, highly directional antenna that they wanted to design. They were thinking about maybe creating this Magnetorquer orientation control system. They wanted to start, design, and build and launch the satellite in 12 months. And they wanted to do it with 100% students. So that's all pretty lofty goals. I scraped through the Twitter feed and the Facebook feed of the program looking for all the photos. And on the left there's one of the prototypes of the highly directional antenna. Kind of looks like a horn. And that's George next to him holding onto one of the, basically a few dev kits strapped together. Hold it closer. Oh, okay. Great. And there's some dev kits of the original transceiver that George is holding there. And the 3D printed prototype there is basically the earliest concept of what they thought it would start looking like. So the club ran like that until probably about mid-2016. Mid-2016, the club actually separated from the University of Melbourne and became a separate entity in and of itself. And at that point, I joined around a little bit before that point, and mid-2016 is kind of after we split off. We sat down and we said, all right, this hasn't really gone anywhere yet. We really need to sit down and buckle down on what the vision of this program is and how we want to do what we're doing. And so I've laid it down here. Basically, the vision was we knew we wanted to develop a student-built satellite. We knew that the whole intent of this was to develop the next generation of space pioneers. And something that we're really snowballing on now with the space agency is to grow the sector. So from that then, we derived out for the ACRUX-1 mission what the mission objectives were. So partial success, and I think just going back to the original goals, it was about setting clear and achievable goals was clear. So partial success was literally just building and launching something into space. It didn't even have to work for us to claim partial success because we knew how much of a challenge it is to get something into space. Success for us was just receiving a single beacon from the satellite in orbit, which means it has to be up there and operating for us to hear from it. And then our stretch goal was 2 weeks of continuous operation in space, and also to validate the orientation control system that we'd built. I'm going to go into a little bit of detail here for those of you who are technically minded. So with spacecrafts, there's 3 main ways that satellites point themselves around in space. Obviously, in a zero-G environment, it's a technically challenging task, right? The first way that most satellites use is called reaction wheels. So you get a weight and you spin it up, and then there's an equal force that pushes you back. It's a flywheel. The second most common is gas thrusters. So you've got a gas canister inside your satellite. You push it out in a certain direction, it spins the satellite in the other direction. You know, every action has an opposite and equal reaction. The third way is using something called magnetorquers. So magnetorquers basically use electromagnets to produce a magnetic field that pushes off the Earth's magnetic field. So you have to be close enough to the Earth to do this. So you have to know where in the Earth's magnetic field you are, and you produce an electromagnetic force against that, and it pushes it slightly. It only gives a tiny little amount of force in the order of micro nanometers, Newton meters. Sorry. So there's a little block diagram. Obviously, the Earth has its magnetic field. We detect where we are in that using a magnetometer. Then also from the Earth, we capture the heat signature of the Earth using infrared sensors. We take both of those through a Kalman filter and control them using a B-dot algorithm, which which also takes what's called a TLE. Basically, the ground station has to send up to the satellite where it is in orbit. And then from all that information, the satellite computes how it needs to push, and then it controls the electromagnets to create that electromagnetic field. And so magnetorquers have been used before, but what was new about how we'd done it was how we sense where the Earth is, and how then we can use that to point it in any arbitrary orientation. Okay, anyway, back to the story. So mid-2016, after that, you can still see the Uni of Melbourne logo here, but we got a new office up in Exhibition Street, kindly from the University of Melbourne. The team grew. There's a bunch of us here. Late 2016 to early 2017, we really started to buckle down on design, and we started to figure out how we wanted to solve these problems. And so on the left, there's the very first prototype that I showed you before, and you can see as it goes right, the design's getting more and more complex as we actually figure out how to design this thing. So mid-2017, team grew even more. This is in the same office. And actually at this point, we had about 60 engineering volunteers working on the program. So they're not all here. There are 60 engineers working on it, and about 20 extra people in the program across things like legal and marketing and comms and everything. Moving on, late 2017, we started to figure out exactly, well, what we thought exactly, how the science need to work to operate in space. So on the left there is one of the simulations of how some of the algorithms work, and on the right is our overall simulation space for how we're anticipating, how the heat affects us, and then how we can orient the satellite in space. Here's us experimenting in the lab. So on the left that's called a Helmholtz cage. So it's essentially an electromagnet, and you can turn up the magnetic field in it to simulate what the Earth's magnetic field looks like. So you can, we'd usually dial it up about 10 times stronger than the Earth's magnetic field, just to start accelerating the simulations and the experiments. And on the right there is the purple lights are simulating how much energy we'll get from the sun. Cool. So by the time early 2018 comes about, we've got a pretty good idea of how this thing will work. We've designed all of the pieces separately, and we're just starting to put the whole thing together. And this is an exploded view of what the satellite ended up looking like. So you can see there's 6 faces. Each face has solar panels on it. We've got magnetorquer rods in the center here. There's 2 lithium batteries underneath. We've got our 32-bit flight computer down the bottom. We've got a bunch of sensors on each face of the satellite, and then sensors inside the satellite as well. The transceiver on the top, and then just above that is our deployable antenna. And something I'd like to point about this is when we're talking about the goals, the primary goal was to have a student-built satellite. And so what usually happens in industry is the developer will buy about 70% of the components off the shelf. Everything that you see here was custom built by the students except the deployable antenna and the transceiver. Everything else was bespoke. So everything from the solar panels to the battery chargers to the power harvester to the flight computer, the electromagnets, it was all designed by us. We literally were wrapping those electromagnets by hand. We designed all the circuit boards ourselves. The mechanical chassis was designed by us as well. the only reason why the transceiver and the antenna didn't work is because when it came down to it, we wouldn't have actually been able to get the whole program together, but in time, if we had built them ourselves. So we had to pull it out at the last minute and put on the off-the-shelf unit. I don't want to talk about this too much because it bores me even looking at it, but you would not believe the licensing and regulatory requirements. It's unbelievable, especially before the Australian Space Agency was founded. It was very much fighting the battle ourselves. So the way that it ended up working is a satellite's classified as a defense item, basically. So you go through ITAR restrictions. And so we have to export our satellite from Australia into the States. We integrate in the States, and then the States ships it over to New Zealand, where we ended up launching the satellite. And then obviously going through frequency allocation and the human casualty analysis, proving that we're not going to hit the ISS and that we're going to burn up in orbit and not hit someone on the head. So that's about mid-2018. By about mid-2018, that was crunch time for us. And we'd really fallen into a good habit of running the project. We'd figured out how to do this thing. How do you get 60 engineering volunteers who volunteer their time between 10 and 40 hours a week to come together to build this sort of thing? We'd fallen into our rhythm, and basically we built the whole organization around the question: what is the most important thing that I can be doing right now? And what's the most important problem that I can be solving? And if you're not solving the most important problem that you possibly can be, go and find that problem. And that's all we care about. We don't care about managing people or writing documents where you don't need to, unless it's solving the problem. So at that point, mid-2018 was the first time we went and did our pilot build. So we said, this is putting it together for the first time. So you can see there's a whole bunch of wires sticking out of this thing. You can see one of the Magnetorquer rods in the middle there. There's the interboard connectors. The mechanical parts are strewn all over. You notice there's no solar panels on here. We had supply issues at that point on this sort of thing. But this is really useful because it's the first time that we'd actually started to put the whole thing together. After that, it was crunch time. When you put it together for the first time, you figure out what's wrong with it. So you find all the bugs, hopefully all the bugs. And so I was trying to think about how do I show a photo of everyone drinking too much coffee and not sleeping enough. And this is as close as I got. So there's some really cool shots. There's people outside testing the ground station antenna. This is again going through the solar tester, making sure we're getting enough energy from the solar panels, and just a bunch of time in the lab. Late 2018 comes around and we finally get to build the real satellite. So that's what it ended up looking like. You can see the batteries here. One of the Magnetorquers on the outside. This is the flight computer up top. The SD cards go up there, and then interboard connectors here. And then so this whole thing obviously sits in the middle of the satellite. That's putting all the solar panels and the mechanical chassis around it. So that same experiment that I showed you before, this is the same thing running again with the actual satellite. So it's kind of the full loop closing, the end-to-end test closing, showing, this is the experiment of the thing we think of how it'll work with some prototype electronics, full through to the final electronics and the final satellite. All right, we finished the design. We have to go and make it compliant and prove out to the launch provider that it's not going to blow up in a vacuum and that we meet all the environmental requirements. So there's one place in Australia you can do this, up in Mount Stromlo in Canberra, and there's one chamber. It's called the Wombat XL, and I had to include this photo because here's our little tiny CubeSat, our little 1U in this huge chamber, and they basically have to get that entire chamber down to the vacuum of space for our tiny little CubeSat. So there it is. So we were supposed to launch in December 2018. That got pushed back to January 2019, then February, then April. Delay, pretty typical. Until finally May came around and we got a solid launch date. So how do you get a satellite from Australia to the States? In hand luggage. So that's Rowan's taking it in a palanquin case on the plane. And then finally integrating it. So that's basically the pod where all the CubeSats, so that's a 3U pod, and that's Rowan integrating it into there. So there are 2 other satellites that sat on top of us. It's in here. Okay, so the big day, 29th of June. So I'm just going to pause for a second and just think about, the program had been running since late, mid 2014, early 2015. And we'd been seriously working on the engineering since about mid 2016. So we've been working on this for about 3 years of our lives, 3 serious years of our lives. And it came down to launch day, which I can tell you there's a huge amount of stress at this point. We're really excited, but there's a lot of stress. This is the Electron rocket. Rocket Lab was obviously our launch provider. They're in New Zealand. So we get to launch day. Launch occurs, launch is successful, we get to T plus 50 minutes. At T plus 50 minutes, this is an animation of basically what happens. So the kick stage deploys us out of the side there. And we got confirmation of, first, the launch was successful, and confirmation from Rocket Lab that the orbital insertion was all fine. And so I was talking about stress before. Imagine the stress of getting up to this point and then realizing that the rocket didn't blow up. Rocket Lab have done their job. They've done everything they need to do. And all of a sudden, it's about us working and us doing our job properly. So our first pass occurs. So the first pass, basically, the rocket deploys us about here. And then as it comes around to the ground station here, we get our first pass. And so your first pass is your best opportunity to hear from your satellite. You haven't been in space for that long, so thermal considerations haven't really started to hit your satellite. You're not too cold, you're not too hot yet. You've probably still got enough power from your batteries, so your solar system doesn't actually have to work. It's basically your best opportunity on your first pass. So the first pass comes up, and radio silence. We don't hear anything. And we're devastated at this point. We're thinking, well, we're not devastated. We're thinking, all right, it's fine. It probably maybe a timer reset or something didn't happen. We'll wait the extra hour and a half, because it takes an hour and a half, obviously, to get back around Melbourne. And we think, okay, the second pass, I'm sure this will be okay. And thank goodness, we got our first packet. And so this is a screenshot of the engineering view of how we got that first packet. And basically, we coded in the message, to do, please tell MSP that their satellite works. Woo! And the ultimate irony of that is that on the day, our ground station actually didn't work. We ended up having a bug where obviously your ground station needs to track the satellite as it goes over, so it's got motors on it to do that. And as the satellite was coming over, someone got a sign wrong in the math. So the satellite's coming over like this, and our ground station's tracking like that. And the best thing about this is there's an organization called SatNog. And SatNog's an amateur radio organization, basically of space enthusiasts who track amateur satellites in orbit. And I gave a talk here April last year, and someone in the Q&A section afterwards said, hey, have you heard about SatNogs? They're this great organization that do this thing. I said, no, I haven't. And we ended up following up and catching up with SatNogs. And then we said, hey, we're launching the satellite, and they ended up tracking the satellite for us on launch day. And the best part about it was, because we didn't hear from it, they did though. And the only reason that we heard from it on that day was because SatNogs heard it. So the full loop has come around. So maybe I'll do more presentations.
The Space Association had a vital part of this program.
That's right. You can claim it. So thanks to SatNogs. Okay, so post-launch, so we had 3 or 4 days of really good data. We were going every pass. We were getting a lot of data from it, from the beacon. And frankly, at that point, we were saying, oh crap, what do we do now? Because in hindsight, my optimism was pretty low. But we were getting really good data. The thermals were really good. We were sitting at about 12 degrees Celsius internally, which is really good. We were charging properly. We're doing everything it should do. It was a bit too early to see how well the magnetalkers would work. Basically, we had to send a command up to it to request that data for it to come back down. But then after the 4 days, what ended up happening is we're energy negative, which we thought we would be. But energy negative basically means that you get less energy from the solar panels than what you use in the satellite. And we expected that. It just means you only operate in the sun. But it looks like we're going through some sort of boot loop. So it's It's running out of charge. Then as it comes up, it waits 5 minutes before the first transmission, and the first transmission happens, and then it's browning out and then resetting itself, and it's doing that. Classic, right? And so basically what we're doing at the moment is there's this ground station with SatNogs in Europe, and we're getting them at morning time in Europe as the satellite goes overhead to send a sleep message. So we say, hey, go to sleep, go into low power mode, and then it charges up in the sun until it gets over to Melbourne. And then when it's in Melbourne, we send up a message saying, hey, turn on, please send me the data. So this is like huge international kind of operational challenge that we've got at the moment. But if that works out, we can continue doing that. We can automate that process and then continue getting more data and then look at the orientation control system. All right, so what's next? So ACRUX-1 was really a concept mission. This is the first time that an amateur organization in Australia has done this since 1970 with Oscar 5. And so there have been a lot of naysayers, myself included, thinking that there's a lot of things that can go wrong with this. So now that we've gone through this proof of concept, it's really about what's next. So the next mission's being planned. There's about 3 missions in the pipeline. Obviously, the next programs are going to be bigger and more challenging. We're going to align with the Space Agency and what they think they're going to be doing and what they think the direction in Australia should be, and solve real problems. So, in summary, 3 years of our lives, and the whole budget ended up being about $300,000. When you think about that, that's actually a phenomenally small amount of money to do what we did, which I think speaks a lot about where space is now. So 3 years of our lives, we're really actually developing space pioneers in Australia. And the reason that I say that is because all the students who are coming out of this thing, they're graduating with master's degrees and everything. And they're basically getting jobs before they can graduate at some of the best companies in Australia. And unfortunately, some of them overseas. But they're really getting some of the best jobs. And now that we've done this once, it's a lot easier to do the next missions. And the way that I see it is, we started off with nothing. We got to here. And then with the framework that we've built up, we can do something even just that exciting again for the next mission. That's it. Thank you.
How easy was it to hitch a ride?
Oh, actually, so I can talk about this now. The last time I was here, I couldn't talk about it. So we went through a third party called Spaceflight. Spaceflight, basically the third party broker, you go to them and say, hey, I want to put my satellite into orbit. And then you pay them a commission, and then they put you on a satellite. So we were originally going to be on a SpaceX mission, SSOA, for those. We were actually originally going to be on that, but then we were going to be in a 600-kilometer orbit, which means we'd decay in 20 years. But there's a space law which says you have to be able to deorbit yourself within 25 years so you don't become space junk. And then we ended up they increased their altitude up to 620 kilometers, which put us over that law. So we had to change it. So with Spaceflight, because we were with this provider, they changed us to the Rocket Lab launch. I don't want to officially say this, but Rocket Lab are a fantastic company, and if you were going to do this, I would recommend going to them directly. Literally open up their website. You can go to rocketlab.com or whatever it is, and there's a button up the top which is book my satellite, and you click that button, and it's almost like going on Uber or something. It's just phenomenally easy. That company is definitely the future of this sort of launch. So now, if you went through that sort of thing, it'd be a lot easier.
So the $300,000 that you talked about, that includes the cost of the launch?
Mm-hmm. It included the licensing, the launch, the engineering development, the fees to pay all the government agencies that we needed to pay, the engineering costs, the flights to go over to all the pizza and the coffee and the beer. Yeah.
2 questions. How did you fund that? And also, is this satellite still up there? When will it deorbit?
It'll deorbit in 3 years because we chose that lower orbit. It's at 450 kilometers. And the first question, mainly from universities, but we offer a lot of value, as I think you can imagine. And so the first mission was mainly through universities, talking about the educational outreach. But in the future, I think it'll be very easy to justify the costs of the program for the amount of value the program delivers.
Of the subsystems you acquired, which were subject to ITAR, and also why was the system subject to ITAR?
So it's basically an ITAR exception. So because satellites are a defense good, you have to prove that you don't have defensive or offensive capabilities. We got audited almost. Someone from defense came and inspected the office to see if we had nuclear capability. And she walked in and she said, "You don't have nuclear capability." You have to do it. Because it's classified as a satellite is classified as a defense good. They have to inspect it to make sure you don't have something on there.
Apart from learning, as you did in the first one, is the Australian Space Agency looking to make the next ACRUX-2 more feasible, easier approach? Are they putting anything towards?
I hope so. I haven't heard. They're changing the rules apparently in September about how you go about the licensing. So for our export license, we basically had to talk directly to the Minister of Innovation to get that license. And so apparently they're changing that in September. I haven't heard about the logistics, but most of the challenge for us was just because we didn't have anyone who could tell us how to do this in Australia. And so what I'm hoping is that now that we've done it, even if the rules are still painful and long, at least then we can say, hey, here's our application, here's how we did it, and then point them in the right direction. Because 95% of your time is figuring out who to ask and what questions to ask. 5% of your time is filling in the forms and paying them the money. It's figuring out what to do the first time. And so we've got this big checklist of all the things that we did. And so hopefully the next time someone wants to do this, we just say, here's our checklist, here's our applications, go and do the same thing. Hopefully.
I haven't checked recently, but 2 weeks after the launch, NORAD had not sorted out what the COSTAR and the NORAD number was for the satellites on that launch. Has that been done now?
So we know what we are because of the phase shifting, and the ground stations could pick out which one we were. But there was a mystery satellite on the launch, which is that what you're talking about? There was a mystery satellite that no one had identified. Rocket Lab hadn't announced, and that won't be identified. So there's a few things that they specifically won't. It's pretty typical. Rocket Lab launched defense satellites, right? So NORAD won't publicly identify what those satellites are.
So will the satellite actually deorbit to Earth, or will it burn up? And what data are you monitoring? Is it just internal data and testing the magnetic propulsion?
Magnetalker. The orbit decays in 3 years, so it'll ish. We're not deorbiting ourselves. We're just waiting for the orbit to decay until we burn up, and that should be in about 3-4 years. What data are we getting? So primarily, it's just about how well the system's working. So thermal data, power data, how well the software is working. There's basically a whole suite of sensor data that we get about the performance of it, and that's really how well have we built it. So then the next time when we do it, do we do the same thing, or what do we change about the next one? And then the other thing, obviously, is how well is the magnetic orientation system working?
What was the cost of the actual launch, and what's the weight of the satellite?
I don't know if I can say our exact launch costs, but it was about a third of the total cost. I found it very good to talk directly to Rocket Lab about these sorts of things. I can't even express how easy it was to deal with them when we needed to deal with them. So they almost said to us, for the next one, tell us what your launch costs should be. It was almost the discussion. Said, nothing.
And was it in New Zealand dollars?
What was it? No, because we went through Spaceflight, right? So,
Okay.
Yeah.
And do they charge by the weight of the satellite?
Yeah, it's like going to the deli. Yeah, it is. You pay by, like, if you're 1U or 2U or 3U, there's an incremental cost for that. I think it'll decay, right? So if 1U is the most expensive per kilo, 2U is less expensive per kilo, but still more.
So what was the weight of your satellite?
1 kilo.
1 kilogram.
Yeah, it was 1U.
On the magnetalkers themselves, what is the intended use? Is the Earth's magnetosphere stable enough that using a magnetalker enables you to actually point a telescope, or is it more just to get in general orientation to change orbits?
So we're hoping we can achieve about ±8 degrees of precision.
So
which isn't good enough for a telescope. It's good enough for anything but a telescope almost. If you want to point down at the Earth, or if you want to track a ground station, it's accurate enough to do that, but not for precision telescopes.
Was there a second chance? If that failed, was that it? Mission over?
Yep. Hence why we define partial success. Hence the stress, right? There wasn't a second chance to do this. We didn't have the funds to build a second one. We didn't have the funds to launch a second one. So I'm very glad it went well.
Like, when is the signal going to fail, do you think, on this current satellite you've got? Or has it failed already? Are you still getting signals from this satellite?
We're not getting data from it, but we are, what we think we're seeing, it looks like we're seeing transmissions that have started, but we're not able to decode them. So if we can revive it with this whole Germany to here, go to sleep mode, then it should operate for the whole 3 years.
Oh, okay.
Yep.
And with the new, your new project, version 2, what do you hope to get out of that project compared to what you've got now? So what's your new project going to involve?
So the vision of the program is still to develop space pioneers, right? It's still to grow the sector. The specific mission itself, we haven't exactly nailed it down. It'll either be an Earth observation, so looking at something like climate change and effects on Australia's climate. There's a lot of interest in that in Australia, especially at the moment, around water monitoring and bushfire monitoring. Other than that, space situational awareness, so dealing with space debris. And there's a few different fields. The Australian Space Agency's outlined 3 main areas that they're thinking, and we're obviously going to align ourselves with that. We haven't defined the exact mission. Like I said, there's about 3 that are floating that we're still trying to nail down, and I think once we nail that down, we'll obviously talk about that, but I don't want to shoot ourselves in the foot until we've exactly figured out the mission.
How space rated was the electronics and things? Was it off the shelf, or was it nuclear bomb proof, or what were you?
So I started this program coming from life-sustaining medical devices, right? So 3 years ago, I came in saying everything needs to be radiation hardened, and we need a 3 microcontroller voting system because it's single fault redundant and coming in with a sledgehammer. What we learnt was actually the biggest risk to the program wasn't radiation, it was us getting something wrong, right? So because of that, we basically changed almost all of the architectures to deal with that main risk. So we made the flight computer incredibly simple. It's a 32-bit, it's an MSP 432, it's a 32-bit Texas Instrument chip, no radiation hardening at all. We've obviously got error checking on memory and things like that, like basic things. We actually originally had radiation shields as well. We had aluminium plates all around the satellite, but they ended up cutting some of the cable harnesses, and it was just a pain to put them together. And we said, it's more likely that we're going to break something because this is so complex. So we actually got rid of all the radiation hardening and radiation shielding.
So if you wanted a longer duration, that might come into effect.
And we're in a really low orbit anyway. We're only at 450 kilometers anyway. So there's not, if we're talking about probability, radiation is about a probability game. And if there's the probability is we'll get one in, 30 years, there's a higher probability that we're going to break something in the first 2 weeks of the thing when it's supposed to work. So that was actually really interesting. We got rid of all the complexity about radiation hardening because we said that wasn't actually really the risk. The real risk was us implementing a complex system and getting something wrong.
Leads nicely into this question. Was it a design issue that caused you to have not enough power to complete the full orbits, or was it performance degrading, not being able to orientate yourself to the sun, or were you weight constrained and just couldn't put enough performance on the satellite?
I can only really theorize what's happening now, and I will. But we thought we'd be energy negative. We basically only had we're basically spot on. We were where the constant power usage of the satellite in normal operation is about 1 watt, which is quite a lot. And we thought we'd be getting around 0.8 watts to 2 watts to 3 watts of energy. And that's basically just, so we thought we'd be energy negative overall. So obviously, because you're only in the sun half of the time and out of the sun half the time, you need to get at least twice as much energy. So we thought we'd be energy negative, but probably what's happening is it's probably just a software issue. So we're boot looping and then the tracking algorithm so the solar panels have a tracking algorithm to get the energy from it. And I think what's probably happening is when we come out of that, it's there's not enough charge to kick in that algorithm quickly enough, and so we're not getting as much power during the boot loop. So what you do is just put it in a sleep mode, so it doesn't consume that power and doesn't make a transmission. We think that's what's happening anyway. Does that make sense?
How long before you find out whether that sleep is going to work?
So the funny thing about this is when we're organizing this, everyone's got full-time jobs now. So the people who are trying to organize this thing with this guy over in Germany, we have to wait until our schedule allows it and his schedule allows it. We have to wait for exactly the right orbit, so it's going over just in the morning in Germany and then just in the evening over Melbourne, which is it's basically just a probability game until our orbit kind of all aligns. And so we've had, I think, one shot at it so far, and that didn't actually work out. It was just that we didn't logistically sort it out. It was kind of a dry run. So we're hoping in the next probably few days to week or two that we'll have a good opportunity. It's just almost a waiting game now.
Just towards the beginning of your talk, you did say something about the wider industry and what their ties were with the space agency and so forth. So, where do you see your organisation going next?
I think we need to align with the Australian Space Agency. They've set out outlines of where they think the Australian industry should go, and that's based on a lot of data and a lot of information that they've received. I think we'll align ourselves with that, definitely. But really the value that we add and the reason why the program exists is to foster the next generation. So then when things like the Apollo missions come around the next time, whether that be to this lunar gateway or going to Mars, that it's sustainable and that we've got a group of engineers and scientists and science communicators and everything that goes along with this, so that we build up enough people to sustain that. And so that's the overall goal. And so there's these three directives. They're saying space situational awareness, Earth monitoring, and GPS, I think it is. And they say that because they've got a lot of information. So obviously we're going to align ourselves with that.
Fantastic. Well, thank you, Blake. Let's put our hands together. That was fantastic. So we went from 50 years history, Apollo 11, to last month. So this is fantastic. This is what really is exciting for us in Australia. Thanks for coming out again. You're serial offender now, so you're on the dance card for the next time.
All right, we'll have to do something cool for the next mission then.
Absolutely.
Excite everyone about it.
Thank you very much. We're going to take a break now, ladies and gentlemen. Stretch your legs, have a drink,